When it comes to automation, timing is literally everything. So today, we're going to pull back the curtain on one of the most essential tools in any programmer's toolkit, the timer on delay, or as you'll hear it called, the TON instruction.
So, just picture a huge factory. You've got these giant motors, conveyor belts that go on forever, and presses that could crush a car. How in the world do you tell one of those presses to just wait for 2 seconds before it comes down? Or make sure a pump runs for exactly 1 minute? Because, you can't just shout, "Hey, hold on!"
And the answer? Well, it's actually really clever. It's all about building in a little bit of patience. You're creating a programmed pause, a little delay right between the go command and the actual action. It sounds simple, but this little step is the secret sauce to making sure everything happens exactly when it's supposed to. And the tool that gives us this superpower is the star of our show today, the timer on delay, the TON timer. Honestly, this thing is the absolute workhorse of industrial control. So what is it really? Well, a TON instruction has one job, and it does it perfectly. It waits. It just sits there watching an input, and only when that input has stayed on for a specific amount of time, a time that you set, will it let something else happen. You can think of it like a digital stopwatch that hits a button the second it reaches its target time.
But, to really get a handle on it, we've got to pop the hood and see what's inside. So let's break this timer down into its most important parts.
Okay, so every TON timer has 3 key values you need to know. First, the timer itself just needs a name, right? Something unique like conveyor_delay_timer. Simple enough. Second is the preset, or PRE. This is your target. This is how long you want the delay to be, and it's almost always in milliseconds. So if you want a 5-second delay, you type in 5,000. And finally, you have the accumulated value, or ACC. This is the running clock. It starts at 0 and just counts up, showing you how much time has actually passed. Now, besides those values, the timer also gives us these 3 little status bits. Think of them like indicator lights on a dashboard that tell you exactly what's happening. The enable bit, or EN, lights up the second the timer gets the signal to start. The timer timing bit, TT, tells you, hey, the clock is running right now. And then there's the most important one, the one we're usually waiting for, the done bit, or DN. That one only turns on when the timer's finished.
All right, so we've got the parameters, we've got the status bits. Let's put it all together and watch how this thing actually works, from the very beginning to the very end. The entire life of a timer really just boils down to 3 big moments. First, when its input turns on and everything kicks off. Second, the moment it finishes counting. And finally, when its input turns off, which is what resets the whole thing back to the start. Okay, phase 1. The input goes true. The very instant the condition to start the timer is met, like, say, a sensor gets blocked, bam, that enable bit turns on. That's your first confirmation. We've received the command. At the exact same time, the timer timing bit also flips on. This is like the green light. It's telling you, okay, the clock is now officially running. So, with both the enable and timer timing bits on, our accumulated values starts its climb. It goes from 0, ticking up millisecond by millisecond, all the way up towards that preset value we gave it. And here it is, the magic moment. The instant that accumulated value equals the preset value, 2 things happen. The timer timing bit turns off because the counting's over, and, more importantly, the done bit turns on. This is the signal we've been waiting for. This is the timer basically yelling, okay, time's up, do the thing. Okay, that's all great in theory, but where does this stuff actually get used? Let's step away from the code and onto the factory floor to see how this simple timer solves some really big, real-world problems. A classic example is staggering motor startups. If you try to fire up 3 massive motors all at once, you get this huge inrush of current that can trip the main breaker and shut the whole place down. So what do? You use a TON timer. Motor 1 starts, and when it's running, that triggers a 5-second timer. When that timer is done, it starts motor 2, which in turn triggers another timer for motor 3. You see the pattern? And the result of this little chain reaction is huge. Instead of one giant power spike that shocks the system, you get these smaller, much more manageable steps. You're basically smoothing out the demand for electricity, which protects all your equipment. It's so simple, but so incredibly important. All right, here's another one that's a little more subtle, switch debounce. When you press a real physical button, the metal contacts inside can kind of bounce for a fraction of a second, creating this messy, flickering signal. A super fast PLC might see that flicker and think you press the button 5 times.
The fix is beautiful. You just put a really short TON timer, like say 200 milliseconds, on that button. Now the PLC will only count it as a press if the signal stays solid for that full 200 milliseconds.
So what you're really doing here is creating a tiny little buffer that acts like a filter. It's just long enough to completely ignore all that messy electrical noise from the bounce. And what you get is what you wanted all along. One clean, reliable signal for every single button press. And for our last example, let's talk about making alarms smarter. Imagine you have a temperature sensor, and it briefly spikes just because someone opened a door and a little steam came out. You don't want the big red alarm to go off and stop the line for a temporary flicker, right? So you set it up like this. When the temperature goes high, it starts a 30-second TON timer. The actual siren is connected to that timer's done bit.
Now, if the temperature goes back to normal before those 30 seconds are up, the timer just resets itself and nothing happens. No alarm, no panic. The siren will only sound if the high temp is a real problem that sticks around for that full half minute. It's all about avoiding those annoying nuisance alarms and making your system smart enough to know a real problem from a temporary hiccup.
So as you can see, from handling the raw power of giant motors to filtering out the tiniest electrical noise, this simple TON timer is all about adding control and intelligence. It's a fundamental building block that lets you create some incredibly clever automations. So that leaves me with one last question for you. Now that you know how to build a pause into any action, what process out there would you want to make just a little bit better?